The neutral must still be bonded to the service disconnect even if it is bonded in the meter socket. The service disconnect provides a convenient and accessible point for disconnecting the neutral when servicing or replacing the panel. According to the National Electrical Code, the neutral must be bonded to the service disconnect. For a service of 100 amps or less, a copper bonding jumper not smaller than number 10 American wire gauge shall be used. For a service over 100 amps, a copper bonding jumper not smaller than the service entrance conductor shall be used. The service also requires a grounding electrode system. This can consist of a driven ground rod, a buried plate, or other electrodes approved by the NEC. The ground wire should be connected to the ground bar inside the service disconnect and routed to the grounding electrode system. Bonding the neutral in both the service disconnect and the meter socket creates multiple paths for neutral current ground. This is not a problem as long as all connections are tight and secure. The NEC does not require that the neutral be bonded at only one location. The original panel that had the neutral bonded to the panel and the service disconnect bonded through the conduit could potentially create objectionable current. This is because the neutral current could flow through both the conduit and the grounded conductor, creating a parallel path and increasing the impedance of the neutral return path. This can lead to voltage drop and overheating of the neutral conductor. To resolve this issue, a proper grounding electrode system must be installed and the neutral bonded to both the service disconnect and the panel. The conduit between the disconnect and panel should not be used as a bonding path for the neutral. When dealing with electrical systems, it's critical to adhere to the National Electrical Code or NEC. Grounding and bonding are two distinct but interconnected concepts that ensure electrical safety. Grounding creates a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protection devices like circuit breakers or fuses. Bonding, on the other hand, connects non-current carrying metal parts to create an electrically conductive path, minimizing voltage differences and reducing the risk of electric shock. In a typical residential electrical service, the neutral conductor is bonded to ground at the service entrance, typically within the main service panel or at the service disconnect. This bonding point establishes the reference point for the electrical system and ensures that all grounded metal parts are at the same potential as the earth. The grounding electrode system, which includes ground rods, ground plates, or connections to metallic water pipes, provides a direct connection to the earth, further enhancing safety. The size of the grounding and bonding conductors is determined by the size of the service entrance conductors, as specified in the NEC. For instance, a 200 amp service would require a larger grounding electrode conductor than a 100 amp service. The NEC provides detailed tables, such as Table 250.66, to determine the appropriate size of the grounding electrode conductor based on the size of the service entrance conductors. When a subpole is installed in a separate building or structure, it's crucial to understand that the neutral and ground conductors must be kept separate. The neutral conductor should not be bonded to the subpanel enclosure. Instead, a separate equipment grounding conductor must be run from the main service panel to the subpanel to provide a grounding path for the subpanel enclosure and any equipment connected to it. This separation of neutral and ground in subpanels prevents circulating neutral currents and minimizes the risk of objectionable current. Objectionable current refers to unwanted current flow on grounding conductors, which can cause nuisance tripping of ground fault circuit interrupters or GFCIs and create potentially hazardous voltage potentials. Multiple grounding paths can contribute to objectionable current, especially if the grounding system is not properly designed or maintained. To mitigate objectionable current, it's essential to ensure that all grounding connections are clean, tight, and properly sized. The grounding electrode system should be inspected periodically to verify its integrity. In some cases, it may be necessary to install additional grounding electrodes or to use specialized grounding techniques to address objectionable current issues. When working with electrical systems, it's always recommended to consult with a qualified electrician to ensure that the installation meets all applicable codes and safety standards. The electrical work can be dangerous, and it's essential to take all necessary precautions to protect yourself and others from electrical hazards. Always de-energize circuits before working on them, and use appropriate personal protective equipment such as insulated gloves and safety glasses. Understanding the principles of grounding and bonding is crucial for ensuring the safety and reliability of electrical systems. By following the NEC guidelines and best practices, you can minimize the risk of electrical shock, fire, and other hazards. Remember to always prioritize safety when working with electricity, and never hesitate to seek professional help if you have any doubts or concerns. The National Electrical Code, specifically Article 250, covers grounding and bonding requirements in detail. It outlines the rules for grounding electrode systems, grounding conductors, bonding jumpers, and equipment grounding conductors. The purpose of grounding is to limit voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines, and to stabilize voltage to earth during normal operation. Effective grounding provides a low impedance path for fault current, allowing overcurrent protection devices to quickly clear the fault and prevent damage or injury. The grounding electrode system typically consists of one or more grounding electrodes connected together to form a comprehensive grounding network. Common grounding electrodes include ground rods, ground plates, metal underground water pipes, and metal building frames. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in Table 250.66 of the NEC. The grounding electrode conductor must be securely connected to the grounding electrode using approved methods such as exothermic welding or listed connectors. Bonding involves connecting all non-current carrying metal parts together to create an electrically conductive path. This includes metal enclosures, metal raceways, metal piping systems, and equipment grounding conductors. The purpose of bonding is to minimize voltage differences between these metal parts and to provide a low impedance path for fault current. Bonding jumpers are used to connect metal parts together, ensuring electrical continuity. The size of the bonding jumpers is determined by the size of the circuit conductors, as specified in Table 250.102 of the NEC. Equipment grounding conductors are used to connect the metal enclosures of electrical equipment to the grounding system. These conductors provide a path for fault current to return to the source, allowing overcurrent protection devices to operate. The size of the equipment grounding conductor is determined by the size of the overcurrent protection device, as specified in Table 250.122 of the NEC. Ground fault circuit interrupters, or GFCIs, are devices that protect against electrical shock by detecting ground faults. A ground fault occurs when current leaks from a circuit to ground, such as when a person comes into contact with a live wire and ground. GFCIs are designed to quickly interrupt the circuit when a ground fault is detected, preventing serious injury or death. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of electric shock. Arc fault circuit interrupters, or AFCIs, are devices that protect against electrical fires by detecting arc faults. An arc fault is an unintentional electrical discharge that can occur in damaged or deteriorated wiring. AFCIs are designed to quickly interrupt the circuit when an arc fault is detected, preventing the arc from igniting nearby materials and causing a fire. AFCIs are required in many locations, such as bedrooms and living rooms, where there is a high risk of electrical fires. Surge protective devices, or SPDs, are devices that protect against voltage surges caused by lightning, power grid switching, or other electrical disturbances. Voltage surges can damage or destroy sensitive electronic equipment. SPD are designed to divert surge current away from the equipment, protecting it from damage. SPD are available in various types and sizes, and they can be installed at the service entrance, at subpanels, or at individual outlets. Regular inspection and maintenance of electrical systems are essential for ensuring safety and reliability. Inspections should be performed by qualified electricians to identify potential hazards, such as damaged wiring, loose connections, or overloaded circuits. Maintenance should include cleaning electrical equipment, tightening connections, and replacing worn or damaged components. Proper grounding and bonding are critical for the safe and reliable operation of electrical systems. By following the NEC guidelines and best practices, you can minimize the risk of electrical shock, fire, and other hazards. Always prioritize safety when working with electricity, and never hesitate to seek professional help if you have any doubts or concerns. Always consult the latest version of the National Electrical Code for the most up-to-date requirements and regulations.